Have you ever wondered how artificial intelligence actually learns? Today, we're diving deep into the fundamental building blocks of AI, the layers in artificial neural networks. By the end of this video, you'll understand exactly how data flows through these layers to create intelligent behavior. Every artificial neural network is built with three primary types of layers, and understanding these is crucial for anyone interested in AI or machine learning. First, we have the input layer. This is where raw data enters the network. Think of it as the front door of your neural network. Second, the hidden layers. This is where the magic happens. These layers perform all the heavy computational work, extracting features and learning incredibly complex patterns. Finally, the output layer. This produces the final predictions or classifications that we actually care about. Let's start with the input layer. This is beautifully simple. It receives raw input data and passes it forward without performing any computations. For example, if you're processing an image, each neuron in the input layer might represent a single pixel value. If your image has pixel values of 255, 128, and 64, those exact values get passed to the next layer unchanged. The input layer is essentially the translator that converts real-world data into a format that neural networks can understand. Now we reach the heart of neural networks, the hidden layers. This is where the real learning happens. Each hidden layer performs a specific mathematical operation. It takes the weighted sum of inputs, adds a bias term, and then applies an activation function. This might sound complex, but the result is powerful. These layers can extract features and learn incredibly complex patterns. You can have one hidden layer or hundreds. Deep learning networks often have many hidden layers, with each layer learning increasingly sophisticated features. The output layer is where predictions are born. The number of neurons here depends on your specific task. For classification problems, you might use a softmax activation function that outputs probabilities for each class, like 80% cat, 15% dog, 5% bird. For binary classification, a sigmoid function works perfectly, giving you a simple yes or no answer. And for regression tasks, where you're predicting continuous values like house prices, you use a linear activation function. Let's explore specific types of hidden layers, starting with dense or fully connected layers. In a dense layer, every single neuron connects to every neuron in the previous and subsequent layers. It's like having a conversation where everyone talks to everyone else. These layers are incredibly versatile and form the backbone of many neural networks. They perform that weighted sum and activation function we discussed, allowing the network to learn complex representations from the input data. Convolutional layers are the superstars of computer vision. Instead of connecting every neuron to every other neuron, they use filters that slide across the input data. Think of these filters as tiny pattern detectors. One filter might detect horizontal edges, another might detect curves, and yet another might detect textures. By combining these detected features, the network can recognize complex objects like faces, cars, or animals. This is why convolutional neural networks are so powerful for image processing tasks. Recurrent layers add something special to neural networks: memory. Unlike other layers that forget previous inputs, recurrent layers maintain information across time steps. This makes them perfect for sequential data like language, speech, or time series analysis. When you're reading this sentence, you need to remember the beginning to understand the end. That's exactly what recurrent layers do. Popular variants include LSTM and GRU networks, which are particularly good at remembering important information while forgetting irrelevant details. Not all layers are about computation. Some are about making our networks smarter and more robust. Dropout layers randomly turn off neurons during training. This might seem counterproductive, but it forces the network to learn more robust features instead of relying too heavily on specific neurons. It's like learning to ride a bike with different parts occasionally not working. You become more adaptable. Pooling layers reduce the spatial dimensions of data, making computations faster while controlling overfitting. Max pooling, for example, takes the maximum value from a small region, preserving the most important information while reducing data size. And there you have it, the complete picture of neural network layers. Remember, input layers receive data, hidden layers extract features and learn patterns, and output layers make predictions. By combining different types of layers, dense, convolutional, recurrent, and regulation layers, we can build specialized architectures for any task. The next time you use voice recognition, image search, or language translation, you'll know exactly what's happening under the hood. Data flowing through these carefully designed layers, each performing its specific role in creating artificial intelligence. If this helped you understand neural network layers, give this video a thumbs up and subscribe for more AI deep dives. What type of neural network architecture would you like to explore next? Let me know in the comments below.